Partial fraction decomposition. Let's go ahead and start by reviewing how to add two rational expressions. So I have 2 over the quantity x plus 1 plus 3 over the quantity x minus 4. To proceed, we're going to need to find the common denominator, which is just the quantity x plus 1 times the quantity x minus 4. So our first fraction is going to be 2 over the quantity x plus 1, and if I multiply the bottom by the quantity x minus 4, I also have to multiply by that on the top. And then we have plus the right fraction, which was 3 over quantity x minus 4. We'll have to multiply the top and bottom by the quantity x plus 1. So now that they have common denominators, I can go ahead and add across the numerator. So I'll have to distribute. I'll have 2x minus 8 plus 3x plus 3 all over the common denominator of x plus 1 times x minus 4. So I end up with, in the numerator, combining like terms, 5x minus 5 all over. On the bottom, if I multiply out those two binomials, I'll get x squared minus 3x minus 4. So we started with 2 over the quantity x plus 1 plus 3 over the quantity x minus 4, and combining those together we got quantity 5x minus 5 all over x squared minus 3x minus 4. So this means that 2 over x plus 1 plus 3 over x minus 4 is the partial fraction decomposition of 5x minus 5 all over x squared minus 3x minus 4. What we're interested in doing is the reverse procedure of what we just did. The reverse procedure of starting with a rational expression and writing it as a sum of two or more fractions with, quote, simpler denominators is called partial fraction decomposition. And the two or more fractions are called partial fractions. So in this section, we're going to be given one rational expression, and in this example, my denominator is a quadratic, and we want to break it down, right, decompose it into the sum of two or more simpler denominator fractions. So these are linear denominators instead of a quadratic denominator. A quick note before we start: to find a partial fraction decomposition, we need a proper rational function. A proper rational function, p of x over q of x, where q of x does not equal 0, has polynomials with degree of p of x, so the degree in the numerator, is less than the degree of the denominator. So if the degree of p of x, the numerator, happens to be greater than or equal to the degree of the denominator q of x, we have an improper rational function, and we must first perform long division. Let's jump into our first example. We want to find the partial fraction decomposition for 3x minus 4 all over x squared minus 2x minus 3. I'm going to start by rewriting the rational expression 3x minus 4 over x squared minus 2x minus 3. And the next step is going to be to factor the denominator if it isn't already factored. So here my denominator is going to factor to x minus 3, x plus 1. So now each of those linear pieces, x minus 3 and then x plus 1, those are going to be the denominators of my partial fractions. So this quotient, this rational function, is going to equal some number, let's call it a, over the linear factor x minus 3 plus some other number b over the linear factor x plus 1. So our job is to find these numerators a and b, these constant terms. Well, the whole idea is that when we add these back together, they should give us our original rational expression. So we're going to go ahead and think about adding these generic pieces back together now. Well, to add it back together, we're going to have that common denominator of x minus 3 times x plus 1, and the a on the top would need to get multiplied by the x plus 1, so we'd have a times the quantity x plus 1, and then the numerator constant b would have to get multiplied by x minus 3, so we have plus b times x minus 3. So again, we're in search of these values a and b, and it has to be true here. We can kind of follow the string of equalities. The denominators are the same, quantity x minus 3, quantity x plus 1. So if we really want these to be equal, we're essentially setting their numerators equal to each other. We want to know what values make 3x minus 4 equal to this a times quantity x plus 1 plus b times quantity x minus 3 scenario. I'm going to go ahead and set the 3x minus 4 equal to a times the quantity x plus 1 plus b times the quantity x minus 3. So now the only way these two can be equal to one another is if we compare all the terms in front of x, and those are all equal to one another. So in other words, on the left-hand side of the equation, I have just a 3 in front of the number x. And on the right-hand side, if I think about distributing in the a, I would have an a in front of x, and then if I distribute the b in, I would have a b in front of x. So here's what I'm going to do to kind of organize my work. I'm going to think about, okay, well, in front of the x terms, so I'm thinking about in front of the x terms, I have a 3. Well, that would have to equal a plus b. So the stuff in front of x on the left would have to equal the stuff in front of x on the right if the left side is truly equal to the right side. And then the constant terms on each side, so on the left side, the constant term, the one without any x's involved at all, is negative 4. And negative 4 would have to equal the constant terms on the right-hand side. Well, the constant terms on the right-hand side are going to be a, because after I distribute the a into each side, I'll have an a there. And then after I distribute the b into both sides, I'll have a minus 3b. So those are going to be all the terms that don't have x's involved. So I'm going to have the constant terms. So I'm going to go ahead and, again, organize my work. The constant terms on the left, negative 4, would have to equal, on the right, a, and then minus 3b. So the stuff that doesn't have any x's associated with it. So after I distribute in the b, negative 3b won't have an x associated with it. After I distribute in the a won't have any x's associated with it. So what I've essentially created here is a system of equations. So I have two variables with two unknowns. I have 3 equals a plus b, and negative 4 equals a minus 3b. So now I have either substitution or elimination that I can use to solve this system of equations. I'm going to choose elimination. I'm going to multiply this top equation by a positive 3 so that when I add it to this bottom equation, it will cancel out my b terms. So here I'm going to go ahead and multiply by positive 3. So my new top equation is going to be 9 equals 3a plus 3b. My bottom equation is still negative 4 equals a minus 3b. So when I add these together, I'm going to have 5 is equal to 4a. And then I'm interested in solving for a and b. That's the whole point, solve for a and b, because we want that decomposed, or those decomposed fractions, the smaller fraction, or simpler fractions. So I'm going to find a by dividing by 4. So I'm going to have 5 over 4 is equal to a. And then I can substitute a into any equation involving a and b. So I'm going to go ahead and substitute 5 over 4 into 3 equals a plus b, that just original equation. So I'll have 3 is equal to 5 over 4 plus b, and I'm going to solve for b. So I have 3, which I'm going to rewrite as 12 over 4, minus 5 over 4 is equal to b. So b is 7 over 4. So what does that mean? My partial fraction decomposition, I was in search of these values a and b, and I just found them. So my partial fraction decomposition is going to be a over x minus 3, so we have 5 over 4 over x minus 3 plus 7 over 4 over x plus 1. But in this case, I don't want to leave a complex fraction, a fraction inside a fraction, so those denominators of 4 are going in the numerator are going to move down to the overall denominator. So it's going to look like 5 over 4 times the quantity x minus 3 plus 7 over 4 times the quantity x plus 1. So this is my partial fraction decomposition. So if we were to add this back together, we would get our original rational expression. Alright, before we move on from this example, I'm going to go over an alternate way to find the values of a and b. So we're still going to work with the idea that 3x minus 4 has to equal the a times x plus 1 plus b times the quantity x minus 3. So we're still going to work with that equation, and we're still trying to find a and b. But instead of solving a system of equations where I set all the stuff in front of x on each side equal to each other, and all the constants, the things that don't have anything to do with x on both sides, equal to each other, we are going to strategically pick x values. So what we're going to go ahead and do is if the left side truly equals the right side, which is what we're operating under, then it should hold no matter what x value we pick. So what we're going to go ahead and do is we are going to choose the x values that will eliminate an entire term on the right hand side if possible, because then that will eliminate either a or b. So focusing in on a times the quantity x plus 1, if I conveniently choose x to be -1, -1 plus 1 will be 0, and that will eliminate my a term. So what I'm going to do is I'm going to start by letting x equal -1. And that's for every x. So the left-hand side becomes 3 times -1 minus 4 equals 0. That's the whole point. That right-hand side, one of those terms should zero out. And then I have just b times -1 minus 3. So on the left, I have -7. On the right, I have -4b. Well, that means I can just go ahead and divide by -4, so I get the value of b is 7/4, which we already knew from solving a system of equations. Now, to find the value of a, we can go back to this original equation and again conveniently choose, so here's my original equation, we can conveniently choose a value that will eliminate the b variable term. Well, that would be a +3. 3 minus 3 is 0, so that will cancel out the right term. So we're going to go ahead and let x equal 3. Now I have 3 times 3 minus 4 equals a times 3 plus 1, and then plus 0. And so what we have on the left is 9 minus 4, which is 5, equals 4a. And then dividing both sides by 4, I get a is equal to 5/4. So we do get the same exact partial fraction decomposition. 5/4 was a, so that goes on top of x minus 3. It's important to keep the same variable, depending on how you labeled it, above the correct denominator. So simplified, we'd have 5 over 4 times the quantity x minus 3 plus 7 over 4 times the quantity x plus 1. So the same answer, but an alternate method. Now my only warning is that while this is simpler, it doesn't always work out. The solving the system of equations method will always work. It just may be more time consuming, and it may be best to do a combination of those two things, as we'll see with further examples. All right, so this now goes through a little bit of the process of finding a partial fraction decomposition for some rational expression, f of x over g of x. So this assumes that we have a proper rational function, and then first we must factor the denominator, and then depending on the factorization of the denominator, we're going to get different partial fractions. So if we get a distinct linear factor, distinct meaning different, if we get different linear factors, ax plus b, then we're going to have a corresponding partial fraction, some constant, a1 over ax plus b, for every distinct or different linear term. That's like the example we just did. We got two different pieces in the denominator, two different factors, so we put a, some constant, above one of them, and b, some other constant above the other one. But there's different possibilities. So what if we get what's called a repeated linear factor? So we get ax plus b to the kth power. Well, then what's going to happen is we're going to have multiple partial fractions. So we're going to need a different constant over the linear factor to the first power, plus a different constant over the linear function to the second power, and we just keep going with this until we get to whatever power it happens to be. So we'll see examples of this because it looks a little more intimidating than it really is. And the other possibility is we don't always get linear factors, we can get irreducible quadratic factors, so quadratics that we can't factor, ax squared plus bx plus c. If that happens, our partial fractions will look like the quadratic, the irreducible quadratic on the bottom, and instead of a constant on the top, we have a linear function on the top. And if we get a repeated irreducible quadratic, then we have those repeated linear over irreducible quadratic up until we get to the power of the irreducible quadratic form. So the big picture here, the big concept behind this page that looks a little intimidating is that if we have a linear term on the bottom, what has to go on top of it is a constant, right? Just one single variable, a number. If we have an irreducible quadratic on the bottom, then what goes on top of it is a generic linear function. So we would have a generic linear function ax plus b, right? So we should know that's a linear type of function. And from there, once we have everything set up, then we're going to have to set up and solve that system of equations to find the missing variables. Let's take a look at another example. We're going to find the partial fraction decomposition for x squared minus x minus 21 all over 2x cubed minus x squared plus 8x minus 4. The first thing we need to do is factor the denominator. So I'm going to do that scratch work sort of off to the side here. So I have 2x cubed minus x squared plus 8x minus 4. And because I have 4 terms here, I'm thinking that I should try factor by grouping. So within the first 2 terms, I can factor out an x squared, and I'm left with 2x minus 1. Between the second 2 terms, I can factor out a positive 4, and I'm left with that 2x minus 1. So that quantity 2x minus 1 is in common in both terms now. So if I factor that out, 2x minus 1, I'm left with x squared plus 4. Well, x squared plus 4 is an irreducible quadratic. I cannot factor it any further. So this is my denominator factored. So my original rational function would look like x squared minus x minus 21 over this linear term, 2x minus 1, times this irreducible quadratic, x squared plus 4. So to set up our partial fraction decomposition, what we need to know is that the linear factor in the denominator gets a generic constant on top. So we'll call that a. And the irreducible quadratic term gets a separate fraction, but above it goes a generic linear term. So a linear term in general, I'm going to call bx plus c. So I'm just continuing to use the letters alphabetically. So I used a first, then my next generic constant was b for the slope of my generic linear term, and then c would be like the y-intercept of my generic linear term. So I'm ultimately solving for a, b, and c. I'm missing all of those constants because I want to complete this partial fraction decomposition. I've created two fractions, but it's missing those values. So what we do is, well, we think about if these two fractions are truly going to equal this one quantity, I should be able to put them back together. Well, if I put them back together, they will have that one common denominator, 2x minus 1 times x squared plus 4. And on the left side, a will get multiplied by x squared plus 4. And on the right side, bx plus c, that entire factor, so I'm going to put it in parentheses, bx plus c would have to get multiplied by 2x minus 1. So 2x minus 1. So now, the numerator, x squared minus x minus 21, that original numerator, will have to equal the a times quantity x squared plus 4 plus quantity bx plus c times quantity 2x minus 1. So that's what I'm going to look at. I want to set those equal to each other to solve for a, b, and c. So I want x squared minus x minus 21 equal to a times quantity x squared plus 4 plus, and then we have bx plus c times quantity 2x minus 1. Now, if we were thinking about trying to maybe use that shortcut method and pick a convenient x that will eliminate maybe this whole first term, if I try to plug something into this x squared plus 4, and try to make it equal 0, there's no real solution to that, because if I take any number and square it, I'm making it positive, and then I'm adding 4, so there's no way that that's going to be equal to 0 ever. Now, we could try it for this second piece over here, so we could go ahead and find a value that makes 2x minus 1 equal 0, so that would actually be positive 1/2, but then the whole thing is that that's supposed to make the problem quicker, and it's not going to make the problem quicker if we have to plug in 1/2 into every x. So here I have 1/2 squared minus 1/2. I'd have to plug in 1/2 here. So it wouldn't really make it a lot simpler. We're still going to have to solve a system of equations anyways. So that isn't the best route here. So we're going to go for setting up that system of equations. And this time on the left-hand side, I have a x squared term, an x term, and a constant term. So what I have to do is I have to think about the coefficient in front of the x squared term on the left, and then what would all the coefficients that are in front of x squared on the right-hand side look like. So here I'm going to again sort of organize my work and think about it as, all right, what's in front of x squared? Well, on the left there's a 1 in front of x squared, and that has to equal all the stuff on the right that's in front of x squared. Now, best case scenario is that we can do this mentally, as we did on the previous one, but if you have to, you can multiply it out to really see all the stuff that's in front of x squared. So let's try to do it first without multiplying it all out, but then I will multiply it all out. So here, if I did distribute in this a, in front of x squared would be a, and then over here on the right hand side I'd have to distribute all this, so bx times 2x would create a 2bx squared, and then my outer would be minus bx, and my inner would be plus 2cx, and my last would be minus c. So the only thing that's going to give me an x squared term is the bx times 2x. So I'd have a 2b in front of x squared, so plus 2b. Now again, I said it all and we'd want to try to mentally think about it, but if you really have to, you can distribute. So you can say this would be ax squared plus 4a plus, this was 2bx squared. Outer would be minus bx, inner would be plus 2cx minus c. So we could just multiply it all out. And now, in front of the x term, so it's like we're done with x squared, now we move on to the x term. Well, if the left side equals the right side, all the stuff in front of x on the left should equal all the stuff in front of x on the right. So in terms of the x term, on the left-hand side, we have a -1 is in front of x. On the right-hand side, well, this was an x squared term. This is a constant. It has no x's. 2bx squared. Now, -bx plus 2cx. So in front of the x terms, I have a -b and a plus 2c. So I have -b and then a plus 2c. And then finally, we're going to go ahead and take a look at the constant terms. So now the ones without any x's. So the constant on the left-hand side is -21. And that's going to have to equal all the terms without any x's on the right. So that's going to be 4a. And then just minus c. So now here is our system of 3 equations with 3 unknowns. We wanted a, b, and c. So these are my 3 equations. And we're not going to have enough space right here, so I'm going to have to clear some space. Alright, so now here we go. There's a lot of different ways to solve systems of equations. What I'm going to go ahead and do here is I'm going to try to create a system of 2 equations with 2 unknowns. So I have this top equation here. It looks really easy for me to isolate a. I can just subtract 2b to the other side. So I'm going to go ahead and write a is equal to 1 minus 2b. And if I now take that a equals 1 minus 2b and I substitute it in to, this a right here in the bottom equation, then the bottom equation will have b and c in it. And this middle equation already has b and c in it, so I'll be able to solve those 2 equations. So I'm going to go ahead and leave the middle equation alone for now. And again, I'm going to substitute my 1 minus 2b into this a right here. So then my bottom equation is going to become -21 equals 4 times 1 minus 2b minus c. So -21 equals 4 minus 8b minus c. I'm going to subtract the 4 to the other side, so -25 equals -8b minus c. So that's my new bottom equation, right, after that substitution was made right there. And so now I'm going to go ahead and use that middle equation, and I'm going to put -1 equals -b plus 2c. So this is my little smaller system of equations now that just involve b and c. So now to solve this system of equations, I'm going to multiply the top equation by a positive 2 to cancel out this c right here, plus 2c. This will be a minus 2c if I multiply that top by a positive 2. So here I'm going to multiply by a positive 2. I'll get -50 equals -16b minus 2c. And the bottom equation was the same, -51 equals -b plus 2c. Now it looks ugly, but nice stuff's going to happen right now. When I add down, I get -51 equals -17b, and that's it because the -2c and the plus 2c cancel. And -17 goes into -51 3 times. So the value of b is 3. And now I can take that value of b being 3 and plug it in to find a, because a was 1 minus 2b. And I can also plug it into this original middle equation, plug in b to find c. So let's go ahead and find a first, just because that one looks a little bit easier. So now a is 1 minus 2 times 3. So 1 minus 6. So a is -5. And then I had 1 was equal to -b plus 2c. So -1 was equal to -b. We found out that b was 3. Plus 2c. So if I add the 3 to the other side, I'm going to get positive 2 equals 2c. So divide both sides by 2, I get c equals 1. So now that we have the values of a, b, and c, we can substitute it into our original partial fraction decomposition setup, which I'm going to copy back down for us. So we originally had, it was a over 2x minus 1, and then plus bx plus c over x squared minus 4. So it's now just replacing those values of a, b, and c. So a was -5, b was +3, and c is 1. So this is my partial fraction decomposition. Now let's try to find the partial fraction decomposition for this rational expression. Well, good thing the denominator is already factored for us, so we know that the original expression is going to be equal to constant a over the linear term x plus 1, and then we have another linear term x minus 2 cubed, and because it's to the third power, we're going to have 3 separate terms with a constant above it to look like b over x minus 2 plus c over quantity x minus 2 squared plus d over quantity x minus 2 cubed. And so then what we would do is go ahead and think about putting these back together, so forming common denominators, and that's going to lead us to having the original expression equal to, let's make it one giant fraction bar with that same common denominator of x plus 1 and quantity x minus 2 cubed. And what's going to happen is a is going to need to get multiplied by the x minus 2 cubed. So we have a times x minus 2 cubed plus b will need to get multiplied by 1 copy of x plus 1. And it already has 1 copy of x minus 2, so 2 extra copies of x minus 2. So we have b times x plus 1 in parentheses, x minus 2 squared, plus c will need 1 copy of quantity x plus 1, 1 quantity x minus 2. So c times x plus 1, x minus 2. And then finally d, to get a common denominator here, I just need the x plus 1 multiplied by d. So now ultimately what we're looking at is figuring out when the numerators are equal to one another. So we're just focusing on these numerators here. So we'll go ahead and clear out all the rest. Alright, so focusing on just this equation here, we can jump straight to just creating a system of equations, but what we can also do is try to use the shortcut of figuring out what to let x equal so that it will cancel a bunch of terms on the right hand side and allow us to solve for these missing a, b, c, and d values. So what we can go ahead and do is start by letting x equal 2 in this equation, and that will go ahead and zero out these first 3 terms over here that have the quantity x minus 2 in it. So if I go ahead and let x equal 2, then what's going to happen on the left hand side is I'm going to plug x equals 2 into each x, and that's going to go ahead and give me, let's see, 24 minus 72, 18 times 4, and then plus 58, 29 times 2, minus 4 is going to be equal to, so plugging a 2 into each of these x's, well, all of these terms with a quantity x minus 2 will zero out, and then we just have will equal d times 2 plus 1 is 3. So we're just going to have this side is 3d. So we can solve for d. We can just go ahead and add up these numbers on the left, and this left-hand side ends up being positive 6 is equal to 3d. So that means d is just equal to 2 after I go ahead and divide by 3. Now similarly, I can cleverly choose a different x value to get rid of 3 of the 4 terms on the right-hand side. I need to be left with all but 1 term if I let x equal -1, because then these terms with quantity x plus 1 in them will zero out. So I'm going to go ahead and let x equal -1 in the entire equation. And so that's going to make this left-hand side be let's see, negative 3, and then minus 18, minus 29, minus 4, so just plugging in a negative 1. And again, these three terms with quantity x plus 1 are gone, so we're just plugging in a negative 1 into this x, so that's going to give me a, and then times negative 1 minus 2, so we have negative 3 cubed, or negative 27. So here on the left-hand side, if we add all these terms together, we're going to end up with negative 54, and then this again was negative 27a. So if I divide by negative 27, I end up getting that a is also 2. So we have found the value of a and the value of d, so we are only missing the values of b and c. So now, unavoidably, I'm going to have to start thinking about this as a system of equations. So I'm going to keep these two values sort of written off to the side here. So I do know that a is equal to 2 and d is equal to 2, and then make some space. So we'll start by considering the coefficient in front of the variable x cubed on the left. So I have just a 3 in front of x cubed on the left-hand side. So that means on the right-hand side of the equation, I need to figure out what would the coefficients be in front of the variable x cubed. And so we don't want to have to expand everything out. We want to be able to think about what would happen if I did sort of start to expand things out. So here, this first term, x minus 2 cubed, if I did start to distribute, I would end up with a times x cubed plus some terms, right? So in front of the x cubed on the right-hand side, I'm going to have an a. From the next term, if I thought about multiplying things out, so I'm just going to put like a parentheses here, then I'd have plus b times, now here, x minus 2 squared, so this part's going to be x squared, times another x, so I'm also, if I distribute it all out, going to have x cubed plus some terms, right? And then if I move on to the third term here, well, I have x plus 1 times x minus 2, so this is only going to give me an x squared. And the last one, I'm only going to have just this x. So this would be like cx squared at the highest, or that would be the highest degree from this term. And this would be x to the first. So the only thing in front of x cubed on the right-hand side is a plus b. So I like to organize my work here and say, well, okay, in front of x cubed, on the left-hand side we have 3, so that 3 would have to equal the stuff in front of x cubed on the right-hand side, which is a plus b. Well, we actually already have the value of a from our previous, like, cleverly choosing x values. So if I go ahead and substitute in the value of a, so we have 2 plus b, I end up getting that b is just equal to 1. So now I have an additional value. B is equal to 1. So the only thing I'm missing is my c value. Now I could go ahead and proceed by finding all the stuff in front of x squared, but that's going to be a lot more work, just kind of thinking I would have to figure out what all these terms are. So the other term I'm going to go ahead and think about is, instead of the x squared term or the x term, I'm going to think about the constant terms on each side. So the constant term on the left-hand side is negative 4. And then let's think about what's going to happen on the right-hand side with the constant terms, the ones that aren't going to have any x's attached to them. Well, here, if I were to multiply all this out, I'm going to have this last term, negative 2, raised to the third power. So I'm going to have x cubed plus some terms, and then at the end, I'm going to have negative 2 cubed, which is a negative 8. So here, there would be plus dot 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 plus negative 8. Sorry to sort of squeeze that in there. And then if I distribute this a in, I'd get ax cubed plus dot 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 minus 8a. So that's, again, a negative 8, so plus negative 8. And then this a would distribute. So the constant term would be negative 8a from this piece. So I have negative 4 equals negative 8a. And then over here, in the second term, let's think about what would happen. So first I'd end up with negative 2 squared after distributing. So it would be a positive 4. And it would be multiplied by this 1 right here. So the last term is just going to be plus 4. And again, if I distribute this b into each term, the last term is going to end up being 4b. So I'm going to have plus 4b, because again, this would be like plus bx cubed plus a bunch of terms plus 4b. And then we will have to think about these last two. They'll have constant terms as well. So if I were to, distribute this out, the last term would be, first, outer, inner, last, it would be minus 2, and then times the c. So I'm going to have minus 2c. And here, this one's simple because this would be plus dx plus d. So now I know that negative 4 is equal to these four terms that involve a, b, c, and d, but I have the values of a, b, and d. So that means I can go ahead and solve for c by substituting in the remaining values. So I have negative 4 is equal to, if I plug in my 2, I'm going to have negative 16. If I plug in my next value, I'm going to get plus 4, because b was 1, minus 2c, we're solving for c, plus d, d was 2. So now we can go ahead and just start adding things up on this side. We're going to have negative 4 is equal to negative 10 minus 2c, or 6 is equal to negative 2c, divide by negative 2, so we have c is equal to negative 3. So I have my coefficients, my a, b, c, and d. That's what we're solving for when finding the partial fraction decomposition. So now we just go ahead and substitute these back into the original breakdown for those parts at the very beginning. So my final answer for the decomposition will be the value of a, 2, that went over x plus 1. Then the value of b was 1, that went over x minus 2. And then plus the value of c is negative 3 over quantity x minus 2 squared. And then plus positive 2 over quantity x minus 2 cubed. This is my partial fraction decomposition. In this example, we'll again find the partial fraction decomposition for this rational function, where again the denominator is already factored, so that works out nicely. So we'll write our rational function, and that's going to have to equal, so this time we're going to have a constant, over the term x, because it's x to the first, it's linear, so we're going to have a constant over x. But this time we have x squared plus 1, which is an irreducible quadratic that is squared. So above an irreducible quadratic has to go a generic linear term. So we'll put bx plus c over the x squared plus 1 irreducible quadratic. But it's a repeated irreducible quadratic, so I'm going to need an x squared plus 1, all that quantity squared in the denominator, and another generic linear term above it, which I'll call dx plus e. And then we're going to have to we'll go ahead and put the right side back together. So we have the left-hand side is going to have to equal just one giant fraction on the right with that common denominator, x times quantity x squared plus 1 squared. The a is going to have to get multiplied by the quantity x squared plus 1 squared. It already has an x on the bottom. The quantity bx plus c in the numerator, which we'll have to put in parentheses, will need to get multiplied by both an x and one extra copy of the irreducible quadratic, quantity x squared plus 1. And then the last term, quantity dx plus e, will just have to get multiplied by an x. So again, we're just going to go ahead and now, since they have the same denominator, focus on the numerator pieces. So we'll just keep those equal to each other. Alright, so we have just a 1 is equal to these three terms on the right. And we could try to think about if it's worth it to cleverly pick a value. And now here, the only value that we could really cleverly choose is x equals 0, because that will zero out these two right-hand terms. So I can go ahead and say, well, let's go ahead and let x equals 0. then the left-hand side is 1. And then the right-hand side, let's see, if we plug in 0 here, that's just going to give us a. So we get one value, a is equal to 1. But that's it. There's nothing I can plug into the irreducible quadratic, or no real number I can plug in, to the irreducible quadratic x squared plus 1 to zero out these two terms. So I'm going to have to move forward and set up a system of equations. So before I do that, I'm going to start to think about, on the right-hand side, what would happen if I start to sort of multiply everything out over here. So here it's sort of unavoidable. So I have 1 is equal to a times, if I distribute this out, I'll get x to the 4th plus 2x squared plus 1. And then here I'll start to at least distribute. Whoops. I have bx plus c times, I'll distribute the x to this term, that's x cubed plus x. And then here we don't have to distribute, I mean we can just kind of think about it. We want to do as little as possible just to sort of think about what would be in front of each x term. So we're going to have to start with x to the 4th, that's the highest x I see, either on the left or on the right hand side. Well, x to the 4th on the left hand side has 0 as its coefficient. So there's only the constant term on the left hand side. So there would be a 0 x to the 4th on the left hand side. So 0 is going to have to equal, on the right hand side, the only thing that'll have x to the 4th from the first term, or is from the first term a, so a x to the 4th, if I distribute in this a. And on the second piece, if I distribute bx times x cubed, I will have a b in front of x to the 4th as well. X times x cubed is x to the 4th. And then we'll move on to the x cubed term, which on the left again would have to have a 0 in front of it since there is no x cubed term. So the coefficient on the left hand side would be 0. On the right hand side, this first term doesn't give us anything regarding x cubed. Let's see the middle term. So we said first was bx to the 4th. Outer was going to give me bx squared. Inner is cx cubed. So we're going to have, so far, c is in front of an x cubed. And then here, if I distribute the x, I'm only going to get an x squared. So it looks like the value of c is just equal to 0. Then we'll move on to the x squared terms. On the left, there is no x squared term, so we have that 0 once again. And now we can go ahead and think about distributing in this a. Well, I'd get a 2a in front of x squared. So the right-hand side will give me a 2a. Here we said outer was going to give us bx squared. So I'd also have a b in front of x squared. And then here, if I distribute the x to dx, a d would be in front of x squared. And then we'll move on to just x. On the left, there is no x's, so we have 0 again. Let's see here, if I distribute the a to the final term, that's a constant. So that's not going to give me an x. And then last here would give me cx, so I'll have a c. And then we said here, distributing the x to e, we'd have an e in front of x. And then finally, we have the constant terms. So on the left-hand side, we actually have a constant term. We have 1 is equal to, now from distributing in here, a times 1, we'd have a constant of a. And then there would be no constant term here. Every time I distribute, there's an x involved. And here, every time I distribute, there's an x involved. So I get that a equals 1 that I got earlier. So this is enough to find all of my missing values. So a is equal to 1. I can plug that in to the first equation. So if a is equal to 1, that means b must be equal to -1, because 1 plus -1 gives me 0. Here, we just have c is equal to 0. That's given. And then let's see. We can solve for d because we have the values of a and b. So if I plug in a is equal to 1 and b is equal to -1, then I have 2 minus 1, so this is 1. So d would also have to be equal to -1. And then here, the value of c is 0, so the only way I can get 0 is if e is also equal to 0. So we have all of our values here, b, c, d, e, and a. So we can substitute them into our original decomposition. So a is 1, so we have 1 over x, plus we had the value of b was -1 and c is 0. So we have -x plus 0, so we won't write that, over x squared plus 1, plus the value of d is -1, and e is 0. So we'll again have a -x plus 0 over quantity x squared plus 1 squared. So we just plug in our values, a through e, into our original partial fraction decomposition to get us started.